Okay, let's do the E&M test from 2004, FRQ number 1. And so here's a neat little diagram they have. Some kind of wire, got a lambda here. I have a conducting material, something like this. And then it says the figure above left shows a hollow, infinite, cylindrical, uncharged, conducting shell. So it's uncharged. Of inner radius R1 and outer radius R2. Okay, that kind of makes sense. An infinite line charge of linear charge density lambda is parallel to its axis but off center. Ooh, it's off center. Ooh, oh, there it is. It's off center. An enlarged cross-section of the cylindrical shell is shown above. On the cross-section above right, sketch the electric field lines, if any, in each of regions 1, 2, and 3. So here's region 1, 2, and 3. Use plus and negative signs to indicate any charge induced on the conductor. So here we've got a positive charge, but it's off center. So it's going to attract negative charge, and that negative charge will be a little bit more crowded here than it is over here. So I'll spread it out a little bit out here. Okay. And so we have all this positive charge here. Now, here's what you have to understand. Field lines when you have an electrostatic condition, the field lines terminate at the surface of the inside surface of the metal, but the field lines are perpendicular to the surface when they get to the surface. So you might have a field line that looks like this, but then you might have a field line that kind of comes out but then curves so it's perpendicular. And it should look fairly symmetrical. Something like that. You can even indicate that these are perpendicular. Now, how do I know that they're more crowded right here? Well, it's closer to the charge. The field's going to be stronger there because it's just closer. But it's got to terminate there, because what do you know about conductors? If you have an electrostatic condition, there can be no there is no electric field inside that conductor. Now, on the outside here, look, these charges had to come from somewhere. So they come from the outside. But that's all they know. They don't really know about the asymmetry on the inside. So the charge on the outside is going to be uniform. Now, one of the things I should do, how many field lines did I draw? 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I should have 10. I think I drew more than 10. But, so they'll start like this. 2, that 10? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So I think that's what I would do right there. Now let's see. Yeah, there we go. So that's pretty close to what I drew. Now, hey, honestly, I didn't look at this before I did this. So, because I actually kind of like making little mistakes in front of you. If I do, just so that we can talk about where my thinking went wrong. This is a little confusing. What I drew right here, I accidentally kind of re-sketched that, so you want to make your sketch very clear. One thing that may have fooled you is you may have drawn these positive charges more crowded to kind of match what's going on the inside. But think about this. There's no way, if there's no electric field on the inside here, there's no way for these charges to know. Also, this has to be an equal potential surface. So if you have these more crowded over here, they'll push each other away, and you'll have a little current going there. Anyway, so there you go. Now part B, it says in the, and I can zoom in. Let's see. It says in the spaces below, rank the electric potentials at A, B, C, D, and E from highest to lowest. 1 equals the highest potential. Well, great. Where is it? So A is out here, and then B, and then C, D. Where's E? I don't see E on here. Oh, E's over here? Oh, okay. Well, let's think about this. I zoomed in too much. So let's take our positive test charge from infinity and push it towards this little tube. So here's infinity. Let's say this is infinity out here. This is not drawn to scale. All right. So I'm pushing this. Ooh, I'm gaining potential. I'm gaining potential. I'm gaining potential until I get to A. And then so A is going to have potential. Then I'm going to gain potential. So A is going to have the lowest potential. So this is the lowest. Then I go inside. Now, there's no electric field to do work against. So B and E are going to be at the same potential, the potential I gained getting to the surface here. Now remember that once you go in, the electric field is 0, but the potential that it took to get there isn't 0. It's just a constant as I move inside the conductor because there's no electric field to do work against. So B and E are going to have the same number. And then I go into C. I had to work against the field. And then to go from here to here, I have to do work against the field. So D is going to have the highest potential. D is going to be 1. And C is going to have the second highest potential, 2. But B and E are going to have the same potential, 3 and 3. And then A is going to have the lowest potential. And there's my answer. And that's how you get to it. Does that make sense to everybody? Even those of you who have your back turned towards me and don't seem to be listening. Okay. This classroom is kind of awkward, but I want you to, you have to look and see what's going on. You have to visualize it. Both this, A and B, are strictly visual problems. You have to understand conceptually what's going on and be able to see it. Okay, there's no computation, there's no equations here. Okay. Now, part C. The shell is replaced by another cylindrical shell that has the same dimensions but is non-conducting and carries a uniform charge density of rho. The infinite line charge, still of charge density positive lambda, is located at the center, as shown. Using Gauss's law, calculate the magnitude of the electric field as a function of the distance r from the center of the shell for each of the following regions. Express your answers in terms of the given quantities and fundamental constants. So when r is less than r1, so we're inside here. Well, I'm just going to redraw it. Here I've got this line. It's represented here with positive lambda. So I'm going to surround this thing with a Gaussian surface, like this. And it's just a cylindrical density. And Gauss's law is E dot dA equals Q enclosed over epsilon naught. Well, E is what I'm looking for. Calculate the magnitude of the electric field. Okay. And then A, what is A? Well, A is this surface area. That's going to be 2 pi r times L. That's the surface area of the outside of this can. So the big idea here is cylindrical charge symmetry using Gauss's law to determine the electric field. So this is E, this is my area. Now, how much charge is enclosed? Well, it's going to be L times lambda. Charge density times how long this wire is over epsilon naught. And this is going to cancel. So E is going to be equal to lambda over 2 pi epsilon naught. And then I always put the variable times 1 over r. And that's my answer. And we did this problem. I mean, this is a very standard kind of problem. Now this one's a little trickier. If you're between R1 and R2 in here, you're in here. So in here somewhere. Let's just draw it in there. So here the problem is going to be figuring out how much charge is enclosed by the Gaussian surface. So it's just going to be E 2 pi r L once again. But now, how much charge is enclosed? Well, it is lambda times L, but plus the charge that's enclosed by this stuff, or that's enclosed in here. Let's look at the cross section right here. Well, we've got how much charge is there. Let's figure that out over here. The charge enclosed from this part is equal. Oh, I'm almost off screen here. Well, it's rho times that volume. Well, what is the volume of this cylinder? Well, it's the area of this. So times the length gives you the volume. So rho, and the volume is going to be pi r squared times L. But that, if I just use pi r squared, that's times L, that's this whole thing right here. What do you have to subtract from it? The volume of this guy. You have to subtract. And that's going to be the charge enclosed in this shaded part of this cylinder. So that makes it kind of long here. Let me rewrite it. E equals, and then we'll go lambda L plus rho pi r squared L minus pi r1 squared L over 2 pi r L. Now I don't see any way to really simplify this except I can cancel out the length because it's in every single term. So I'm just going to leave it like this. Plus, I guess you could factor out, you go rho times pi times r squared minus r1 squared over 2 pi r. Is that how they left it? And, oh, yeah, epsilon naught. I always leave that on, epsilon naught. Thank you. Now, how did they leave it? Yeah, I mean, it's the same thing, just slightly different form. Now, here we have the R on the outside. So it's going to be the same thing, E 2 pi r L equals, but this is going to be all of the charge now, which is going to be lambda times L. That's the charge on this guy. And then I need the charge of all of this, which is going to look very similar to this, but it's going to be plus rho times pi r2 squared times L, and then minus the volume of the hole. Over epsilon naught. And so I guess I can just cancel out the L right now. And then E, therefore, is going to be equal to lambda plus rho times pi times r2 squared minus r1 squared all over 2 pi epsilon naught, and I'll put the 1 over r over here. So there's Gauss's law. So the big idea here is using Gauss's law, and remember the tricky part of using Gauss's law. Well, first of all, you got to recognize what kind of symmetry you have. You're going to have 3 symmetries. Planar symmetry, rarely. Spherical symmetry, very likely, or cylindrical symmetry, very likely. This problem is cylindrical. So the area of my Gaussian surface is the curved part of this can or this cylinder, this part right here. So you need to know the area of that is the circumference times the length. And then how to figure out how much charge is enclosed by that Gaussian surface. Any questions? Okay, that is all.